Okay, so what I've got here, this drawing, calculating a rolled and folded saddle bracket. So you can see in the picture here, I've got this bracket here that's been made out of, actually out of 6mm by 50mm wide steel. The one I'm doing in the drawing, this one here, is actually made out of 8mm stock by 75mm wide. So what we want to do is take our main drawing, and the best thing you can always do when you try to make these brackets is draw them out and actually break them down into their constituent components. So, you know, we've got a straight here at A, the bend for B, straight for C, a bend all the way around here for D, straight for E, F for the bend, and G for the bend as well. So I've got that here. It's exactly the same bracket. You can see that A and G are exactly the same length. C and E are exactly the same length. The bends on the corners, B and F, are exactly the same length. And this large rolled surface here is in a separate colour. So the bend, I've broken it into its constituent parts: straight, bend, bend, and straight. So if you can draw it out on a piece of paper, it's going to help you immensely when you start putting your dimensions down as to what you're actually trying to achieve. So here's the bracket itself. The dimension across the bottom for both sides, the bracket is uniform. So from the very end to the inside of the bracket, this face here is 60mm on both sides. I'm using a 12mm radius. The overall height from the very top to the very bottom is 173, and the internal radius is 85mm. So we're going to keep working with those dimensions, obviously, all the way through. So we'll come right back to the start. Now, just for some reinforcement, what V-block size to use for folding different thicknesses of material. So the V width for folding mild steel is 8 times the material thickness. So 8 times 8 is 64mm. So I'd come down this chart here. This is off the press brake that I have at work. So that V right at the very top there needs to be 64mm wide. And if we come down the V for V chart down to here, 65, they're recommending a radius of 10.8. As I said, I'm using 12mm. If you come across on the chart just out to here, you've got these 5 figures. The very middle one is actually for 8mm. So that's how that corresponds. So they're recommending 10.8. But what I've done is I've made up my own tooling. So I've got this piece of steel here, 24mm in diameter. So half of 24 means the radius is actually going to be 12mm, which is going to give us the radius for the corner. So that's just the, instead of using a dogleg blade and a 64mm V, I might add too that this V here currently is sitting at 50mm. I've just put this mock up here so you can actually see it. So 12mm for the radius for the throat instead of the 10.8 on their chart. I just wanted to put that in there once again to show you how to do it. So I've got the chart of this table written up, or this method for doing it, calculating the lengths and the fold position. So the material thickness is 8mm mild steel. The V width, if you were using the chart, would be 65mm. The radius from the press brake chart, oh, sorry, I've actually gone, okay, so I've got to make a mistake on there, haha. That says 10.8, but I'm doing it at 12, and that's why it's got 12 in there. So the formula for a single corner is 2 times pi times bracket radius times half the thickness, close bracket, all divided by 4. So the top of the line, 2 times pi times radius times half thickness, or plus half thickness, is for a full 360-degree circle. By dividing it by 4, we do a portion for a 90-degree corner. So this is a 90-degree corner of a full 360-degree circle. So we would divide it by 4. So there's my calculation, corner calculation. 2 times pi times 12 millimeters plus half the material thickness. The material thickness was 8. So 4 millimeters. Do that calculation, divide it by 4, and we get 25.13 millimeters. I've rounded it to 25 millimeters. Obvious reason, you're not going to be able to use a scriber and a square to 0.13 of a millimeter. So I've got to be sensible about it. Formula for the rolled section. If you look at the formula, the top line is exactly the same. I have merely divided it by 2 here because if we look at it as a full circle, we're using half of it. So where we had 4 in this formula for a 90-degree corner, dividing a full 360-degree circle gives me 180 degrees, and that's what that is. It's half of a circle. So that's why it's done by 2. So the formula for the rolled section is 2 times pi times the radius, which is 85 millimeters, plus half the material thickness, which was 4, close bracket, divided by 2, and we get 279.6. I've left it at 0.6. It's close to 0.5. We'd try and work to half a millimeter, so that's perfectly acceptable. So that distance, if we go to this one, from the end of C all the way around to E is 279.6 millimeters. So I'll put that into the chart. Got my letters down the side here, A, B, C, D, E, F, G. So A and G are exactly the same. If we go into this, the distance between those 2 lines is 60 millimeters. We have to take off the material thickness here, 8 millimeters, and then we take off the radius. So that's what we're taking off. So 60 millimeters minus 8 millimeters minus 12 for the radius means that A, which is from that distance to there, so the straight line distance before we start the bend, is 60 minus 8 minus 12 leaves us with 40 millimeters. In the chart you can see I have got 40 millimeters for A and 40 millimeters for G. So the next one will be C. Have I got that in there? Yes, I have. C and E. So C and E. So if we go into the chart again, so here's C on this side and E on this side, both exactly the same length. So in order to determine those lengths, we've got 173 right from the very top of the arch, and all the way to the bottom is 173. So what do we need to take off? Well, we take off the 8 millimeters material thickness there, and then we take off our radius, because that comes all the way down to this point here, down to this red line here, which I've just stuck in. So we've got 8 mil, we've got 85 millimeters. At the bottom, we've got the material thickness, and we've got the radius. So we've got 8 plus 12 plus 85 plus 8. So we'll go back into the front chart. I've got 173 minus 2 times 8, which is 2 times the material thickness, minus 85 millimeters, minus 12 millimeters for the radius, leaves 60 millimeters. So C and E are 60 millimeters long. Okay, so D, what am I doing here? D, I have automatically put in the calculation from here, 279.6, put it in here. So add them all together, 40, 25, 60, 279.6, 60, 25, 40, gives us a total length of 529.6 millimeters. That is the length that we're going to go and cut our piece of steel at, 75 millimeters wide by 8 millimeters thick at 529.6 millimeters long. And we can start marking off these lengths, A, B, C, D, E, F, G. So down here, I've got my piece of steel. Turn on some dimensions. There you can see it. I've laid it out. First one from here to here is 40 millimeters. That's the flat, which is A. From A, obviously, to there is B. That's that portion around there, and it's actually working to that mean line, that red line. It's not working to the throat or to the heel. It's working to the mean line. So that is 25 millimeters. The next distance from C was 60 millimeters. This one in here. Then going from these two little points here, this red line here to this red line here, right around that arch on that mean line, that red line is 279.6, and then we're laying in our lines back out the other way, 60, 25 and 40. So it's a uniform length, and there's our piece of steel laid out the exact size with our A in this one. Let's put that on. A in this portion, B here, C, D, E, F, and G. So, fold line positions. Well, if we go into, which one have I got it in? This one here. You can see that fold line positions. This line here is actually at 45 degrees. So our fold line, our first fold line from the end here is A, which was 40 millimeters. This line here was 25 millimeters long, and half of 25 is 12 and a half. So into our drawing, front page, if we look at what I've got here in the chart, fold line number 1 is A plus half of B. Oh, have I marked that wrong? I have too. Look at that. Have I gone and put that on the chart? So there's always some mistakes on these things, simply because, yeah, okay, so it's only wrong on the chart. Do I want to fix that on the fly? I'm going to fix that on the fly on another screen. Just give me a moment. It's just bringing it up, and I need to change that to, what did I say, 52.5. 52.5. Save that, update that chart. There we go. So there we go. Number 1. Sorry about that. You just got to do this on the fly because there's a lot of work involved. A plus half of B is 52.5. The next point for 2, which is the start point. So I've said that this red line here is the start of the curve, which it is, and it's going to go around to this point here. So I've given those 2 positions. I might actually turn those on right at this point here. Turn this on here. Where are we? There. So there's the first one. As you can see, I got my 52.5 right on the drawing. So that was the first fold. So position number 2, that red line there, is clearly all of A, all of B, and all of C. So you can see I've done that on the chart here. I've got A plus B plus C, which gives us 125 millimeters. So from the very end here to the start of the curve, and I've written this rolled portion, this is where it starts and this is where it goes to here. So that, as you can see, that dimension between those 2 points there is that 279.6. So it comes in from the end, 404.6, just on the chart there. Sorry, point number 3, where the curve ends up here. Number 3 is all of A, all of B, all of C, all of D, 404.6. Point number 4, which is Where have I got it? This one here. Point number 4 is F, or half of F. So we would have all of A, B, C, D, E, and half of F for the fold line, for the last fold line on the last side. So if we go back into our chart, you can see that I've written that A plus B plus C plus D plus E plus half of F gives us 477.1 millimeters. I left that 0.1 in simply to show that I was trying to be accurate. You would simply mark it to 477. So there's our folded out bar, or our flat blank. Now clearly, if you look at it, the large curve is rolled from the inside and the two folds are actually on the outside. So if we look at the drawing, we could say that the two red lines are on the other side of the drawing, or the other side of the piece of steel, which is going to be, and on this side you would roll between these two pieces here. 85 millimeters is quite a tight radius on a piece of 8mm steel. You'd have to have some reasonably strong rollers to roll that. They're very difficult to roll as well. I've rolled quite a few brackets like this, and you have to do a bit of work with a hammer to get them. You know, your rollers can sometimes roll past your start and your finish points, and you have to do a bit of hammer work roughly where the joints are to get this uniform curve here. Quite difficult at times, and you might be able to do your folds after, or maybe they have to be done first depending on what sort of equipment you've got. But that's pretty much how you calculate. That is how you calculate, not pretty much. I got these some drawings here for bar benders, or some photos here for bar benders. Having done the calculation for a press brake, you know, if you were going to do it on a bar bender, you clearly, you know, this is the holding block, this point with the arm on it. You'd put your steel down through here and clamp it in place with this clamp, nice and tight, and it's going to radius around this corner. If you're going to do a 90-degree turn, it's going to come around this corner. It's got a sharp corner on this end. This one actually has a radius on this end. This other one sitting beside it has got a sharp corner and a sharp corner on the other end. In actual fact, the round corner here is for folding rod. Rod, if you fold it on a sharp corner, either of these two corners here or this corner, actually notches the corner and mangles it over time. So the radius is actually for doing rod. So if you were doing flat bar, you're going to have to put a piece of flat bar into one of these and do a fold. And you know, it depends on how tight you put that clamp on it. If you don't do it up to the same tension all the time, you're going to get a different radius. So they're not going to be not as accurate as they would be if they were done on a press brake, where you've got a lot of control over the width of the V and the radius bar that you're using. So I've just put these in for comparison. Now the other thing I want to talk about is if I put a piece of bar in here and I've marked across it with my fold positions that I've got on this drawing. Let me just zoom into this, sorry, mucking around a wee bit. These two red lines, if I'm going to fold those, well, you're going to scratch them on with a scriber and a square. When you come to the press brake, if you've got a large radius bar like I've made, it's actually going to cover your mark up. You're not going to be able to see it. Excuse me. The best thing to do is actually mark an offset from the center of your forming bar to the actual edge of the V block. Now on this chart here, I have got this box here, says the center of the V to the front edge of the V block. Well, I said to you that this is a mock-up and I've used a 50mm V. From the center of the V to the edge of the press brake is 55.5mm. So once you've marked your line across your plate, you can measure across to the width, across to the front of the press brake, 55mm, and put another line, and every time you step up to do your fold, you actually line your 55.5mm offset up with the front of the press, and that way you can get an accurate fold every single time. You're simply not going to see it in here. If you use a dogleg blade, you can get a greater degree of accuracy. Of course you can. But it's just a method for trying to line it up at this point, and you know it's going to be hitting on the fold every single time accurately. So where am I heading? I'm going back to the beginning. Pretty much covered everything, I think. Calculations there. You need to think about the information that you would be putting into the equations. But as you can see, once again, I've talked about this before, it's only addition and subtraction, multiplication and division. These equations aren't excessively hard. They need practice. You need to, you need to sit down or make these sorts of things, 10, 12 times to really gain some confidence and retain the knowledge. If you just do them one every now and then, it makes it very difficult to actually learn and retain the knowledge. So like everything in life, they require a wee bit of practice, but they're actually very, very straightforward, and there's not much to them. So there you go. There's a drawing on calculating a rolled and folded saddle bracket. Everything on the page there. Come back to it, refer to it a few times, and have a go and see how you go with it. Thank you.